Hello, welcome back to the second part of solutions. So I have a graph here, probably a look or figure. It looks a bit like if you remember the Born-Haber process for lattice energies. So the idea is for exothermic solutions here on the left, we have the solution and solvent together, and then we separate them. That's to break their intermolecular forces. Then we mix them together, and if this process is exothermic, that's how it goes. And then on the right here, same idea, but when you bring them together, if it's the net is higher in energy, then it's endothermic. So here are some examples. So where the solute, the solution form is exothermic. There are two of them, lithium bromide and potassium hydroxide, and I can tell you, well, sodium hydroxide gets really hot. So if you ever make a sodium hydroxide solution, to be careful, that sucker gets really, really hot. And here's the opposite, ammonium nitrate and silver nitrate. You can use some of these, usually more ammonium nitrate for icy cold packs. So it's very endothermic. And then here's the ones that are about the same. So sodium chloride is slightly endothermic, but it's close to that. Okay, so let's use some terminology here. And here I have salt, sodium chloride salt, dissolving, turning into sodium ion and chloride anion in water, aqueous. If a solution is saturated, that means no more will dissolve. And salt, sodium chloride salt is very soluble. If you ever try to make a solution, you can put a lot of salt in water. It's about 3 to 1, so 25% solution thereabout is, and that's by mass. You can put a lot of salt in the water. Unsaturated means no more will dissolve. So to make a saturated solution, unsaturated, and so a saturated solution takes a lot of time. Unsaturated, most solutions, the ocean water, for instance, is unsaturated. It just means more can dissolve. And supersaturated, if you up the temperature, then more will dissolve, and then we said that solution is supersaturated. You can use it to grow crystals. It's also how you make rock candy. So you take sucrose, and you make a supersaturated solution. As it cools down, you can grow sucrose crystals, also known as rock candy. Here is a figure. So if you look on the y-axis, you have solubility. X-axis is temperature, and you can see that pretty much everything, there's an outlier there with cerium sulfate, but basically everything, when you add energy to it, add increased temperature, solubility goes up. Okay, well, what about gases? So gases are the opposite. You increase the temperature, the solubility goes down. But then again, the increase the pressure, solubility goes up. And the reason for this is entropy. So gases have higher entropy than liquids, so increasing the temperature is going to drive them out of solution. And then here we have Henry's law. Solubility of gas is the Henry's law constant times the pressure of the gas. And Henry did this quite a bit for scuba diving. And among other things, he suggested using helium instead of nitrogen in drop my calculator. In mixtures to prevent the bends. Okay, so what pressure of carbon dioxide is required to keep the carbon dioxide concentration of a bottle of club soda at 0.12 molar at 25 degrees Celsius? So, solubility is Henry's constant times pressure. So if we look at solving for pressure, so pressure is equal to solubility over Henry's law constant. Our solubility is 0.12 molar, and 3.4 times 10 to the minus 2 molar per atmosphere. And what is that? Let me throw that in my calculator. 0.12 divided by 3.4 e minus 2. I get 3, how many sig figs we have? 2 sig figs, so 3.5 atmospheres. So it seems pretty straightforward. Let's see if you can do this. So try this by yourself. What is the concentration of ammonia when the pressure of ammonia is 0.1 atmospheres? So I'll go ahead and solve this for you. Solubility is pressure times Henry's Law's constant, 0.1 atmospheres times 58 molar per atmosphere. So that's going to be 5.8. Okay, so let's talk about different types of concentration. You should be fairly familiar with molarity. Molarity is moles per liter. Next, we'll talk about molality. Molality is going to be important when we talk about certain colligative properties. That's coming up next. Some of them, like boiling point elevation and freezing point depression, involve molality. Mole fraction, molality is moles per kilograms. Mole fraction, this is known as the amount of the number of moles of whatever over the total number of moles. Mole percent is just a mole fraction times 100. Parts by mass, this is the mass of whatever you're looking at over the total mass, multiplied by something. If it's a percent, it's times 100. If it's parts per million, it's times a million. If it's parts per billion, it's times a billion. And then parts by volume, it's the volume of whatever you're looking at over the total volume. And a special case for proof with alcohol, it's twice the volume percent. So 80 proof is 40%. Okay, so let's do this. So we're preparing a solution by dissolving 17.2 grams ethylene glycol in a half a kilogram of water. The final volume of the solution is 515 milliliters. Calculate the concentration in terms of each one. So ethylene glycol is 62 grams per mole, and that's 0.277 moles of ethylene glycol. Okay, so the first one, moles per liter, it's going to be 0.277 moles over 515 milliliters, 0.515 liters. And what is that? So 0.277 divided by 0.515. And this is 0.538 molar. Okay? And then the next one is going to be moles ethylene glycol, 0.277 moles over kilogram solvent, 0.5 kilograms. So 277 divided by 0.5. And this is 0.554, 0.554, and this is little m molal. And notice that the molarity and the molality are not the same. So there is a slight difference there. And then percent mass. So mass ethylene glycol over total mass. So it's 17.2 grams, and a half a kilogram is 500 grams. 500 grams plus 17.2 grams. So this is 17.2. Divided by the quantity, 17.2 plus 500. And so percent by mass, this is 0.0326. Then times 100% is going to be 3.26%. Okay, and then mole fraction, moles ethylene glycol over total moles. So the mole fraction is the moles ethylene glycol over total moles. So there already mentioned 77 moles ethylene glycol. So we got to put that. But we also have water, and we have 500 grams of water. And water is 18 grams per mole. So if you do that, this is going to be 0.00987 times 100% is 0.98. 0.987 mole percent. So Oh, it's d mole fraction. Oh, sorry. This is mole fraction. This one is mole fraction. Mole percent is 0.987%. All right. So why don't you try it with sucrose? So give it a try. Okay, so that's what you should have gotten if you tried it out. Okay, so the last thing we're going to talk about is colligative properties. We'll talk about this next lecture as well. But a colligative property is something that depends on the number of particles. So the examples of these include vapor pressure, deposition, freezing point, depression, boiling point elevation, and osmotic pressure. So for instance, if you see here, there is ethylene glycol. Ethylene glycol acts as one particle. Sodium chloride, when you look at colligative properties, you have to multiply the number of moles of sodium chloride by 2 because sodium chloride breaks out into 2 particles. Magnesium chloride here is going to break into 3 particles. So that's going to affect each of those properties that way. And to give you an example of something, so if you have a closed system, so if you have a beaker, shown here on the left, you have a beaker, and then you have a pure solvent, and then you have a concentrated solution, and when you close a system, like here it looks like you put like a cake cover over it or something, what's going to happen over time is the solution will dilute on the right. So the concentrated solution will become more dilute. And this is in part, well, this is to tie in to show you vapor pressure, because when you put stuff into solution like that, you lower the total vapor pressure or something, and that's where we can pick up in the next lecture.